Okay, so we're going to start something new chapter. And the basic topic is on electric fields of distributed charges. So we know how to deal with the electric field of a point charge, okay, and we know how to deal with multiple point charges or things like dipoles. We just apply superposition, add up the electric field due to all the individual point charges or charged particles. But what if we have a situation like this? Let's say you have a rod, or like a thin rod, maybe a thin piece of plastic, and we saw in some of the demos last week where I rubbed some sort of material over the plastic and was able to create a charge on it. Okay, so let's say we have some charge, positive charge that's uniformly spread over the entire object. Okay. So we have a complicated or macroscopic object that has a charge distribution on it. And we want to find the electric field of this that's made by this positively charged object. Could we treat this like a point charge? Can we just use the point charge formula in this case to say if we want to find the electric field at this point? Would that be a valid formula to use? Just say 1 over 4 pi epsilon 0 q over r squared? No, that's not going to work, right? Because it's not a point. It's some extended object, and you have some part of it over on one side, other parts over on the other side. And so, what R do you use, and how do you actually deal with that is going to be tricky. So it wouldn't be a valid approximation to say it's a point charge. But how would we deal with this? What might be a general strategy we could use to try to calculate? Yeah. Okay, so you're saying, let me see if I can understand. You're saying that if I move farther and farther away, okay, the point with respect to the object. So here's the object. Oh, okay, I see what you're saying. Okay, so you're saying that clearly, because let's say this part of it is closer to our observation location, that's going to have a bigger effect than somewhere over here. Okay, so one approximation might be, okay, we can just kind of treat this part as having a bigger effect than this part. And that's certainly true. And of course, the farther away you get, the bigger that R is going to be, and so the smaller the field would be due to those individual charges, right? But they're still going to have some effect, right? I mean, this segment might have some create some large electric field, but then there's sort of the segment right next to it, and then we'd have to think about, well, how do we deal with that? And then as we get farther and farther away, how do we deal with the electric fields due to each part? But there's some general strategy where we're thinking about parts of the object rather than the object as a whole, right? So what if I broke it up into pieces? What if I say there's a part, and there's a part, and there's a part? I just treat these as little chunks. It's still not perfect, but what approximation could you use now? How could you deal with those little chunks? Okay, you can assume they're all point charges. Okay, it wouldn't be a great approximation, but it might be a lot better than assuming the whole thing is a point charge, right? So, as was said, this sort of chunk that we treat like a point charge would have a bigger effect than this little chunk, or this little chunk, which is farther away. But we know how to deal with those individual chunks if we treat them like point charges. And if we treat each one like a point charge and find the electric field at each of those chunks, then to get the net electric field, we just add them up, right? Use superposition principle, okay? So we're using the superposition principle to deal with these distributions of charge, okay? And so we're going to have a general procedure. So how to deal with finding the electric field, the net electric field of distributed charges. And step number one is divide the object into pieces where each has a charge, some small amount of charge. We'll call that charge delta Q. Okay, so if Q is the total charge of the object, then a delta Q, or a little change in the amount of charge, or a little piece of the charge, so we're going to call the charge of a single segment of that object. Okay. Now, sort of in going along with that, you want to then draw the electric field due to that individual piece. We'll call that delta E. Okay, draw delta E due to a typical piece, just to get a sense of how one piece of it makes an electric field, and then we think about adding them up. Second step is write an expression for the electric field of one piece. Third is add up the delta E's, the electric field contributions due to all the pieces. And depending on what you're given, there may be a number of different ways of doing this. We might just do sort of a brute force calculation. We might tell a computer to do this repetitive calculation, or we might be able to come up with an analytic way of solving for a general expression. And then finally, check the result. And there may be various ways that we can check to see if the result we get is reasonable. So let's try it. Let's try an example using this uniformly charged segment. Let me draw coordinate axis here. So here's the y direction. Some of this. Here's the y direction. Here's the x direction. And we have a segment, or a rod, sort of a thin rod that has a uniform charge spread over it, and it's lying along the x-axis, and the origin is at the center of the rod. Okay, and let's say the length is 0.6 meters. Okay, so this end is 0.3 meters away, and this end is 0.3 meters away from the origin. And I want to find the electric field due to this, and let's say it's positively charged, has a uniform positive charge. We'll say the total charge is, what do we want to make it? Let's make it 12 nanocoulombs, which is 12 times 10 to the minus 9 coulombs. And I want to find the electric field at some observation location. Let's make our observation location, say here, which is 0.1, 0.2, 0 meters. Okay, so we're trying to find, this is the observation location, trying to find the electric field at that location. So step one is divide it into pieces. And so we have to choose how many pieces we want. Let's choose for right now. Let's say we want to divide it up into 6 pieces. So here is 1 piece, 2, 3, and then another 1, 2, and 3 there. Each piece, so we'll say N, capital N will be the number of pieces we have. And so that's 6. Delta Q then is going to be what? How much is going to be the charge of one piece? 2 nanocoulombs, right? It's going to be Q, the total Q divided by N, or 2 times 10 to the minus 9 coulombs. Okay. How how long is each piece? If this whole thing has a length of 0.6 meters, then I'll call the length of one little piece delta x. And that delta x is equal to what? L over n, right? 0.1. Okay. I want to treat each of these pieces like a point charge. And so where do I want to measure, if I'm measuring that r vector in the formula 1 over 4 pi epsilon 0 q over r squared times r hat. What would be the best choice to measure the r vector? Or what, for instance, if I'm choosing this piece here and I want to draw an r vector that points from where to where? From the middle of the block to the observation location, right? So I want to figure out what that location is. So what is the, what's the coordinates of that location? This is 0.3 meters, and each piece is 0.1 meters long. So this is 0.2, this is 0.1, and so the center would have to be 0.25, right? So we have 0, 0.25, 0, 0 meters, and then this center is 0.15. Okay, and here we have x equal to 0.05, and then we start going the opposite direction. So we have negative 0.05 meters for x, negative 1.5 meters, and negative 2.5 meters. Okay, comma 0, comma 0. I'm just drawing the writing the x components. Okay, so we know where these locations are, and let's just, as it says, draw a typical delta E. We know that, let's say if I pick location here, let's see, this is at 0.15, this is at 0.1, so we're kind of on this side of the observation location. I draw the r vector that points from that location to the observation location, and the electric field points away, right? So that would be 1 delta E. And then the trick is to find all the delta E's due to each individual segment and then add them up, okay? Let's do one of these all together. Let's start with, let's say, what do we want to do? Let's start with this segment. Start with this end segment. So I'm going to find the delta E due to the segment negative 2.500 meters. Okay, so I find first I find the r vector. R is equal to the observation location, which is 0.1, 0.20 minus negative 2.500 meters. So that gives us what? We have, oh, sorry, 0.25. 0.25, thank you. So we have 0.35, right? Sorry. 0.35. And then 0.2 minus 0 is 0.20 meters. Okay? So that's R. Everybody take out a calculator. Calculate the magnitude of R. What do we get? 0.403. We agree? Anybody else get the same result? Okay, 0.403. Next, we have to find r hat. So we have 0.35 over 0.403, comma 0.2 over 0.403, comma 0. And that gives us what? 0.868? 0.868, comma 0.496, comma 0. Okay? Next, we're going to have the electric field due to that segment. So we have the expression, which we should have done in the second step, right? The expression. It's going to be 1 over 4 pi epsilon 0. delta Q over r squared times r hat, right? Treating each like a point charge. So we have 9 times 10 to the 9th. We have a delta Q of 2 times 10 to the minus 9. We have an R of 0.403, so that's going to be 0.403 meters squared. And we're multiplying that by the unit vector 0.868, comma, 0.496, comma, 0. Okay? So multiply it all out. What do we get for the electric field vector? 96.2. Okay, so we have 96.2, comma, 54, 55.0, comma 0, and the units are newtons per coulomb. Agree? We all get the same thing? Does this work? Yes, no? Okay. So let's just check it. We get an x component that's positive, a y component that's positive, and 0. So it looks like it's working out, right? Because we should get a electric field that points away from that segment. So that delta E is going to be pointing in that direction. And then we'd have to move on to the next segment and calculate that delta E. And then we have to move on to the next segment and calculate that delta E and do it for all 6 segments. And so doing this by hand is going to be long and tedious and boring, right? But let's see if we can at least make sense of or try to anticipate what the result's going to be. What do you think when I add all those segments up, what's going to be the direction of the electric field? Kind of point with your fingers. Straight up? Well, we're kind of off axis, aren't we? Which side is contributing more to the electric field? Yeah, that side. So it's going to be, yeah, kind of like that, isn't it? Because think about this. Here is this observation location. Let me erase some of this. This observation location is right in between this point and this point. If I add those 2 segments together, what's going to happen? What's going to happen to the x components? They'd cancel out, wouldn't they? So these 2 should just contribute something pointing straight up. Then I move on to the next 2 segments beside them. And so they're also right in between, symmetrically on either side, far away from this midpoint here. Add those 2 together, and their x components cancel out. And so all you have left over for contributing x components is these 2 segments on this side. So we should get something that looks kind of like that, okay, for the net electric field. Well, doing this by hand is a pain. So let's see if we can do it on a computer instead. Okay, let's see. I've got it set to length is 0.6. Number of segments, we wanted 6 segments. Charge is 12 times 10 to the minus 9 coulombs. Our observation location is on here somewhere, I believe. Observation location is 0.1, comma 0.2, comma 0. And so it should be the exact same setup. So let's run this. Okay, so here's our charge rod lying along the x-axis. And I'll break it up into 6 pieces. Okay, so we're just treating each piece like a point charge. So there are 6 spheres there to represent the point charge. Let's calculate the electric field of piece number 1. And I think it's printing out also these field values. So let's see if we... 96.2, comma 54.96, comma 0. Okay, so we got the correct result for delta E number 1. Keep going. So this green vector is the R vector. This orangish vector is the delta E due to that single piece alone. Okay. Move on to the next piece. We'd have a slightly smaller distance, slightly bigger delta E for that piece. Move on to the next piece. Get a delta E there. Move on to that piece. Get a larger delta E. Move on to the next piece. And now we're on the opposite side. So you see how the x component shifts sign. Same for that thing. And when we add these all together, we get a field so large that it's off the scale here. So we're getting a direction that looks about right. Okay, and let's see what the results were numerically. And I'm not sure if this text is big enough for everybody to see, but okay, so here was the first delta E that we got, that we calculated. And then look when you get to segment number 4, we have 102.7, 410.9, 0. And then when you go past that point, we got negative 102.7, 410.9. So the x component, as we said, shifted, or just changed sign. Y component stayed the same. And so these, from segment 3 to segment 6, the x components are all canceling out. We're only getting y components. And so segment 1 and 2 were the only ones that contributed a net x component. And so the net electric field we got was 233.3, 1447.2, 0 newtons per coulomb. Okay? So that's the basic idea. How would you make a more accurate prediction? What could you do? More of them, more segments, smaller segments, right? So more smaller segments. So let's try this. 233.3, 1447.2. Okay, so let's try it now with, 12 segments. Double the number. So there's 12 little point charges. And now each of these is contributing a much smaller delta E per point charge because it's a much smaller, or half as much charge. And we calculate the total, and we get an electric field that looks almost the same, at least graphically. Let's see what we got. Compare 233.3 with our new value, which is down here, 233.8. So the x component didn't change much at all. New value for the y component, 1,442.8 rather than 1,447 compared to 1,442.8. Okay, so even as many as 6 segments, 10, 12 segments is enough to get fairly reasonable accuracy, and you can just keep testing the accuracy by seeing how many segments do you need to get to a significant digit that isn't changing anymore, right? The fourth significant digit changed, but the third one didn't. So if you only need 3 significant digits of accuracy, 6, 7, 8 segments, probably good enough, okay? So you don't need a lot of segments to get a reasonable prediction depending on what the distances are. You could use as many as 100. And then we're going to be here all day, right, counting up all these. So I'm not going to do that, but you get the idea, okay? More segments, more accuracy, but for reasonable accuracy, you might not need all that many, okay? We're essentially doing numerical integration. Questions here?